Here I will present our recent work on chiral anomaly effects in pulsar magnetospheres. The work was done in collaboration with Edward Gorbar, and it was submitted to the arXiv in October last year. Neutron stars are the well-known laboratories for matter under extreme conditions. Since the theoretical prediction and experimental observation, the neutron stars have been studied a lot. We know that they are rapidly rotating, very dense, and strongly magnetized. In this talk, I will concentrate primarily on the magnetospheres of pulsars, which are made of hot plasma. The main claim of this talk will be that the anomalous chiral plasma can be produced in magnetosphere and can affect the pulsar activity. Now, what is chiral plasma? Relativistic plasma is usually considered to be chiral if it can allow a chiral asymmetry to exist on macroscopic time and distance scales. The chiral asymmetry is when the density of the left-handed and right-handed particles are not equal. In the case of a chiral plasma, it is convenient to describe it in terms of the two densities, the total density and R plus and L, and the chiral density, which is the difference of the two. The first one is governed by the usual continuity equation, which represents the exact conservation of the charge, while the other one is described by the anomalous continuity relation. There are two terms on the right-hand side that violate the conservation of the chiral charge. The first one is the famous quantum chiral anomaly, while the second one is the chirality flipping that happens due to non-zero mass of the fermions in the plasma. In the case of the pulsars, magnetosphere is co-rotating with the star, and it is also highly conducting. Because of the high conductivity of the plasma, the co-moving electrical field in magnetosphere must vanish. That implies that the electrical field parallel to the magnetic field in the laboratory frame must be vanishing. This condition cannot be always sustained in a co-rotating magnetosphere. In fact, intermittently, the gaps or the rips should happen in the magnetosphere due to the charge or current starvation in that magnetosphere. Those gaps will close by the production of E plus E minus plasma, which is induced by the passing background photons in the gap. The parameters of the gap have been estimated since 1975 by Rudderman and Sutherland. And the values for the size of the gap H and the electrical field in the gap is given by the corresponding estimates, and the size is macroscopic on the order of meters, and the electrical field is about 10 to negative 8 of the electrical critical value of the field. Now, in the presence of such an electrical field, E parallel, basically the presence of parallel electric and magnetic fields implies that the chiral anomaly becomes active, and that produces a chiral charge density in the gap. The chirality flipping, of course, will tend to wash away the chiral charge, which is produced by the anomaly. And one reaches the steady state solution with the value of the chiral charge, which is proportional to the chiral anomaly, the source, and inversely proportional to the chirality flipping, which washes away that chirality. The estimates for the chirality flipping rate are well known in the literature. Now, it is important to estimate the corresponding time scales, and it happens to be that the time for the formation of the gap is much longer than the chiral charge production rate time, and therefore the chirality production happens nearly instantaneously, and nearly instantaneously the steady state solution is achieved. That implies that we can estimate the value of the chiral charge in the gap regions relatively easily by using the estimates for the parallel electric field and the known rates for the chirality flipping in the relativistic electron-positron plasma. We can also use that result to estimate the value of the chiral chemical potential, which is very important for the next consideration. Now, in the presence of the chiral chemical potential, the so-called chiral magnetic effect will start acting in the plasma. The essence of the effect is the additional contribution to the electrical current, local current density in the plasma. The coefficient, which is chiral magnetic conductivity, is proportional to the chiral chemical potential μ5 that was estimated on the previous slide. In the presence of such chiral magnetic effect, The plasma is known to develop the chiral plasma instability. One can see this by considering Maxwell equations for the helical modes in the plasma that satisfy the corresponding equation. And the chiral magnetic effect term is highlighted by the box in the next two equations. In the presence of the chiral magnetic effect, the corresponding frequency of the modes are given by the solutions omega-1 and omega-2. In order to understand them better, it is instructive to consider the limit of highly conducting plasma. Sigma goes to infinity, and one finds that the two frequencies are given by the following relations. The first mode is totally damped, and it's due to the charge screening of the modes in the plasma, while the second mode is actually unusual. It is unstable. It can be generated spontaneously for the wave vectors k, which are smaller than a certain critical value for a given helicity lambda. The value of k star can be very easily estimated from the chiral chemical potential that we obtained earlier. For the pulsars with different values of magnetic fields, the key parameters that have been discussed are given in this table. Skipping this, I will concentrate on the physics implications of the chiral plasma instability in such gap regions of the pulsars. Because of the chiral plasma instability, we know that the helical modes will be spontaneously generated. The range of frequencies in which they are induced spontaneously will be spanning a wide window of frequencies between radio and infrared, near infrared range. These modes carry sufficient amount of energy. The total amount of the energy could be estimated. It's proportional to the chiral chemical potential squared, temperature squared, and the size of the gap. And the value of the energy on the order of 10 to 25th ergs is sufficient to affect fast radio bursts and the activity of pulsars. Therefore, to summarize, this work implies that the chiral charge production can be substantial in the gap regions of strongly magnetized pulsar magnetospheres. The chiral charge produced this way can trigger plasma instability, and in turn, that will lead to the emission of helical waves in a wide range of frequencies. The corresponding anomalous physics can be also connected to observable features of fast radio bursts. However, there are several quantitative effects that, while promising, still deserve further investigations. And here I outline several key problems that have to be addressed before a better quantitative estimate of all the physics can be done more carefully. So one has to study more carefully the interplay of the chiral charge production and the E plus E minus pair production in the gaps due to the energetic photons. The chirality flip rate has to be re-evaluated in the presence of very strong magnetic field. So far, we use the estimates for the chirality flipping rate at zero magnetic field. However, the additional suppression of the chirality flipping rate in the presence of magnetic field can be substantial, and in fact, it can enhance the chirality production in the gap regions. One, of course, requires to perform self-consistent simulation of chiral plasma in the gap regions, as the plasma dynamics is rather complicated to rely purely on those quantitative effects. Now, it also has to be studied how the energy is transferred from the unstable helical modes to the observed emission that is seen as, for example, fast radio bursts. And that is all I have to say in this talk. Thank you.